Hello everyone, my name is Priyanka and I welcome you all to my session. Let's read a question which says us to state Lenz's law and give one example to illustrate this law. And the Lenz is a consequence of the principle of energy conservation. We have to justify this statement. And then further we have to derive an expression for the inductance of two long coaxial solenoids but having different radii and different number of turns. So let's first state Lenz's law, which I have already written for you. So Lenz's law, the polarity of the induced EMF is such that it opposes the change in the magnetic flux responsible for its production. So always remember that it means to say is that this induced EMF is always opposing the cause of its production. So let's try to see an illustration for this. For that, let's take a coil. So we're going to take a coil and then we are going to bring a bar magnet near to it. Why are these lines dashed? Because this part of the coil is below the plane. So when we bring the north pole of the bar magnet towards the coil, the magnetic flux linked with it increases. The current is induced in the coil in such a direction that it opposes the increase in flux. This is possible only when the current induced in the coil is in anti-clockwise direction. So the current is going to be formed or is going to flow in an anti-clockwise direction with respect to the observer on the side of the bar magnet. The magnetic moment M associated with this induced current has north polarity towards the north pole of the approaching bar magnet. That means this end is going to be the north and this end is going to be the south. Similarly, when north pole of the bar magnet is moved away from the coil, so let's draw it first. Let's take this as a coil and then that's your bar magnet. Here it was north, south, and we are going to take it away. The magnetic flux linked with the coil decreases. To counter this decrease in the magnetic flux, current induced in the coil is in the clockwise direction, so that its north pole faces the receding north pole of the bar magnet. So in this case, this is going to be the north and this is going to be the south. Now we have to justify the statement that Lenz's law is the consequence of principle of energy conservation. For this, let's make a circuit which is having a coil of few turns and it is connected to a sensitive galvanometer. So we're going to make a coil and then we are going to connect it to a sensitive galvanometer. Now what we are going to do is that we are going to bring a bar magnet near to this coil. It is having north here and south in this direction. So when north pole of the bar magnet is moved towards the coil, the upper face of the coil acquires north polarity. That means here it is going to be forming a north in this direction. Therefore, work has to be done against the force of repulsion in bringing the magnet closer to the coil. Similarly, when north pole of the magnet is moved away, the south polarity develops on the upper face of the coil. Therefore, work has to be done against the force of attraction in taking the magnet away from the coil. It is this mechanical work done in moving the magnet with respect to the coil that changes into electrical energy producing induced current. Thus, energy is just being transformed here. When we do not move the magnet, work done is zero. Therefore, induced current is also not produced. So I'll just repeat what I said, and I'm going to write it down as well, that it is this mechanical work done in moving the magnet with respect to the coil that changes into electrical energy producing induced current. So basically we are saying that the mechanical work done is converting the basically mechanical energy is getting converted to electrical energy. Therefore, it is in accordance with the principle of energy conservation.